Hey there, friends, and welcome to another episode in our Geology 101 Physical Geology series. I'm Geology Professor Shawn Willsey. Thanks for joining me. Today, in episode 13, we'll be covering volcanic hazards. This geology series I put together is totally based on the class I teach here at the college. It's the same curriculum, the same topics. The only thing missing are the labs and the field trips, but you can supplement those a bit with some of my other videos that are here on my YouTube channel. So thanks for joining me, and let's get right to it. Of course, it would be a good idea to make sure you've seen the previous two episodes at a minimum. We are going through things in this series sequentially, building upon our knowledge as we go. In the last two episodes, we looked at the nature of volcanoes, looked at different types of volcanoes, magma systems and such. And now we're going to look at what volcanoes do that cause hazards to people and property. What is the downside of volcanoes? What are the things that society and humanity has to deal with when it comes to volcanoes? And before we get to sort of these things that might seem quite negative, I think it's worth pointing out that volcanoes are incredibly valuable and essential to our Earth in terms of generating our atmosphere, an essential part of the water cycle, recycling chemicals into the atmosphere. We really couldn't exist without volcanoes. They bring diamonds up to the surface, so have that for what it's worth. So we're going to look at volcanic hazards. This is a nice simple diagram from the USGS. This depicts a stratovolcano, as we learned last time, and this shows several hazards associated with this specific type of volcano. Realizing, of course, that every volcano is different magma systems, different eruptive behaviors, and therefore we get different types of volcanic hazards associated with any given volcano. But of course, if we have communities and societies living close to these volcanoes, it's imperative that we understand what these volcanic hazards are and how we can best manage and mitigate their risks and deal with them. So that we're not going to cover all the volcanic hazards shown here on this diagram, but we're going to stick to some of the main ones here. The pyroclastic flows are sometimes called the pyroclastic density currents. We'll look at lahars. We'll talk about lava flows as a hazard, ash fall. What else will we cover? And I think a few others as well, gases and such. So let's go ahead and get right to it. And let's start with perhaps I think the most terrifying volcanic hazard on the list by far to me is a pyroclastic flow, this avalanche of hot ash, gas, sometimes bits of rocks that is barreling down across the landscape at high temperatures and high speeds. There's just several different ways that we can actually have these triggered, and we'll look at these here in a second. But yeah, this is actually quite a terrifying scene, is to have this huge billowing cloud of hot ash come barreling across the landscape. I believe this photo was taken in the Philippines. I'm not sure how that all played out and how this scene ended. You can see the little car here speeding away. Oftentimes these things are moving faster than you can in your vehicle, so they don't always end well. So let's look at these in a little bit more detail. There's a couple different ways that we get these forming. And I had a little error on the last slide there. This is a better list of the triggers or the types of the processes that trigger pyroclastic flows. They're associated with the explosive volcanoes. So these would be our naughty volcanoes, stratovolcanoes, lava domes, and calderas are the main types of volcanoes that are going to produce these. So more of a silica-rich magma composition, intermediate to felsic in terms of silica or magma compositions. And one way here, we'll start with the top of the list, is a column collapse. So when we get a typical eruption from something like a stratovolcano, we get a big billowing cloud right above the vent, right above the volcano of volcanic ash. And that is the eruption column. As long as the pressure at the vent is pushing that ash out of the vent and the upward force provides the buoyancy, we get this big billowing cloud. But as that pressure wanes, as maybe the eruption starts to die down a little bit, a lot of this ash material, some might be carried by the prevailing winds, but a lot of this might actually start falling and descending and moving down the flanks of the volcano and generating these pyroclastic flows. And when you have air sinking like this, that's a compressional event. The molecules are in collision, and so it heats it up even more so. As the air is rising and the ash is rising, it tends to cool off. But as it descends and goes in the opposite direction, it actually heats up, goes down these these concave, sides, the flanks of these stratovolcanoes, and then can move out across the landscape several miles or kilometers. So this would be a column collapse that triggers a pyroclastic flow. Another way you might trigger a pyroclastic flow is just by having the pressure in the gases in the magma just decrease enough that it just sort of boils over, just like the lava, or excuse me, the ash coming out of this eruptive vent just sort of oozes out the top and then speeds down the side. So similar to the eruption column, but no real collapse of the eruption column. It's just basically rising and convecting out and then speeding out down the sides of the volcano. A third process here is dome collapse. So we can have a lava dome, a volcanic dome. That's one of the volcanoes we studied in our last episode. And this lava dome we know is unstable. It's sticky, pasty lava that just oozes up like toothpaste, if you will. If you just imagine just, squeezing toothpaste through a little slit, you just end up with this big glob of toothpaste. And think of lava with that same kind of consistency. At some point it becomes oversteepened, part of the dome collapses, and that can trigger a pyroclastic flow in that direction down one side. And in parentheses here we have just historic eruptions where we've seen exactly that type of behavior produce pyroclastic flows. And then the last one here is a lateral blast, which we saw in the 1980 eruption of Mount St. Helens. So this was an instructive eruption because it behaved a little bit differently than we thought volcanoes behave. We thought that most behave like this, where they erupt basically upwards, right? But Mount St. Helens in 1980 preferentially had magma intruding on one side of it, on the north side, causing the whole north face of the mountain to swell, oversteepen, and then the sequence of events was basically an earthquake, which caused a large landslide, the biggest landslide in recorded history, that moved down off the flank of the mountain. And that reduction in pressure is what allowed the magma to then, and the gases in the magma to just come out of solution and trigger the eruption. So this was an eruption where the eruption was sort of sideways. It was directed more horizontally or laterally than it was vertically. And that action in and of itself generated this massive pyroclastic flow that flowed out tens of miles across the landscape to the north. And we'll look at some video here as well, just so we can get a concept of how these things look. And so let's check out this little video here of a pyroclastic flow. Now these are in Indonesia, and these are relatively small, and they probably look not that harmless, but they behave much like an avalanche. But this is all ash, and this is during the daytime, obviously, so it doesn't maybe look that hot, but at night you would see some red and orange incandescent glow within this billowing cloud of ash. So this is fairly small, and I don't recommend anyone go and try to chase pyroclastic flows and catch them on film. But that gives you a little sense of kind of how they behave as they move down the flank of the volcano. Here's another one here. You can see the high speeds that they move. They often sort of ride on a little cushion of air, a low friction surface, so that allows them to move quite quickly. But these are, it's more than, it's not water vapor. This isn't just gas. This is ash and rock particles. This would hit you like a brick wall. A very violent and destructive volcanic hazard. So some footage there of a pyroclastic flow. If we skip ahead in the video a little bit, eventually we get to what's causing all these pyroclastic flows. And this is the lava dome at the top of Mount Merapi. And so you can see a little collapse right there. And so it's these collapses of the lava dome, this sticky, this looks like rock, and it is basically, but it actually is welling up, and there's lava that's causing it to oversteepen at times. If we move a little bit further ahead in the video clip, they show the lava dome collapsing at night. And so when it collapses at night, you can see that incandescent glow sort of through the ash clouds and the pyroclastic flows. So you can actually see some of that glow there. So just to show you that this actually is lava, this is just low viscosity or silica-rich or felsic lava that's feeding these eruptions. So pretty incredible, these pyroclastic flows, and definitely one of the more serious hazards we have associated with volcanoes. Okay, continuing on. in our look at volcanic hazards. Let's go to the next one here, and that's a lahar. So this would be a volcanic mudflow, and it could be either hot or cold in terms of its temperature. Unlike a pyroclastic flow, lahars can travel much further. So pyroclastic flows, maybe 10 miles or 16 kilometers away from the summit. That would be about the furthest extent of most pyroclastic flows, and usually much closer than that. But lahars can move tens of miles, tens of kilometers away from the vent. You can see some of the numbers there in terms of the speeds, the depth. And the idea here is you're either melting some of the ice cap, if there's snow and ice on the summit area of the volcano, like with a Mount Rainier, let's say, you can melt some of that summit ice and mobilize that water down the flank of the volcano, through the gullies and drainages that come off of the volcano, and that stuff essentially becomes a flood, but it has a lot of sediment load to it. And if an eruption's part of the triggering mechanism, it can also have a lot of ash and debris as well. So it might be triggered by melting of snow and ice. It might be triggered by rainfall, heavy rainfall onto a landscape with a fresh blanket of ash and eruptive material. That can trigger one of these lahars as well. Quick little video clip that shows you some lahar behavior here. So this is back again in Indonesia. And again, these are somewhat small, but you can see the logs, the debris. So again, much like a flash flood, but with a more significant sediment loads, especially of ash particles and tephra. So you can see these things moving down. These obviously, a little small at the smaller end of the spectrum. We don't have, where's the YouTube footage of the truly massive lahars and pyroclastic flows? Those are not good things to go chase and try to record. So that's why a lot of that video doesn't exist. So gives you a little bit of an idea there what a lahar looks like. Okay, next volcanic hazard. So we kind of started with the worst ones here. Oh, here real quick, in speaking about lahars, this is a lahar hazard map for Mount Rainier. So this is in Washington near Seattle, south of Seattle. And what you can see here is this is a USGS hazard map. So they've recognized the drainages that emanate from Mount Rainier, the pathways that lahars would and have in the past traveled. There's a number of communities that lie along the path of these drainages and possible lahar paths. And so a lot of these communities practice lahar drills. They actually have evacuation and hazard plans to deal with the threat of lahars. There's actually a lahar detection system that can let communities know that a lahar along a given drainage has been initiated. And so the nice thing with this hazard, though, is there's some time, right? So it takes maybe 40 minutes to an hour to maybe 2 hours for the lahar to travel from its source area around the mountain down these drainages and into the communities. So for some communities, this type of hazard is the real deal. Explosive volcanoes also produce a lot of ash. The ash can be carried downwind. At some point, that ash will settle and fall out of the sky typically and be spread over a large area. Ash is nasty stuff to get on a building, to get onto the crops, with aviation and aircraft. It can cripple that transportation infrastructure. It's also a bad health hazard. Breathing it in is actually very bad on your lungs and some of your respiratory organs. And so ashfall can be a hazard as well. If there's enough of it on the roof of a home, it can cause that to collapse. It can be hazardous to people and lethal in large quantities. If a community was in the middle of harvest season or growing crops and you put several centimeters or inches of ash on those crops, that could completely be have a huge economic impact as well. So ashfall over a region can be a big deal. This is a map showing you where we have seen some of the truly big eruptions. So here is Mount St. Helens near the upper left corner of the map here, and the little dotted pattern is the area where appreciable ash fell out of the sky from the Mount St. Helens eruption in 1980. And just giving that a little bit of context when compared to some of the truly big eruptions that go back into, the prehistory, if you will, the 2 million year old Yellowstone eruption. You can see sort of the size of that. the Long Valley caldera in California. You can see its extent. And so some of these huge eruptions that thankfully don't happen very often can produce ash and have a significant and measurable ash fall, over 1,000 miles away from its source. So, down here in Texas, they've actually excavated and found measurable amounts of ash that they can trace back through the chemistry and the age back to the Yellowstone eruption. And then, of course, if we can quantify the thickness of the ash over this region, and we can measure its extent aerially, then that gives us an estimate of the volume, how much ash was actually put into the atmosphere during that eruptive period. So ashfall for really big eruptions is a big hazard. And even for moderate sized eruptions like Mount St. Helens, for some of these communities that were to the east and downwind, that was a significant event. Lava flows as a hazard, not as big of a deal, tends to be more of a property hazard. Bottom photo here is the Canary Islands in, I think that was 2021 or 2022. Here's some kids in Hawaii watching a lava flow kind of inching through their neighborhood here. But the good news is we can get people out of harm's way. The lava speed is usually not very high, and so people can get out of harm's way. But of course, property and infrastructure can be in the way, and that can be can have a big negative economic impact from that. And this just goes to better planning, right? Once we know there's a volcanic hazard in a region, maybe something like a lava flow, maybe we can look and see, well, what are the pathways that lava flow might take? Let's look at the topography. Let's not build the critical infrastructure in the path of a possible eruption. Let's try to put those buildings, if we need to, in some place that's more likely to be out of harm's way. So lava flows, another hazard associated with volcanoes. Gases are a threat to all volcanoes. These can be quite lethal to both people and animals, as you can see with the photo of the livestock here. And what's interesting too about gases is you don't necessarily even need an eruption for this hazard to exist. You can have just a volcano that is dormant or not really doing much, but it's constantly, those gases that are down in the magma system are constantly trying to rise. They're working their way through cracks. They might be getting into the local water supplies, maybe a lake, springs, streams, and so they're making their way out to the surface. And one of the gases that causes a lot of problems is CO2. Carbon dioxide is odorless and colorless, and so you can't see it, you can't smell it. It's denser than air, so it settles into low-lying areas. And in some communities, you've got the town or the village at the bottom of the mountain, at the base, at the lowest point, and gases can escape from the volcano, seep down the mountain, and form a toxic and lethal blanket of CO2. Some of the other gases, hydrogen sulfide, water vapor comes out of volcanoes, and then sulfur dioxide along with fluorine and chloric acids, or chlorine, these are acids as well, that come out of volcanoes. So so gases, there's several different episodes where people have been killed by volcanoes, even with a quiet kind of phase where it's not really erupting, just some of the gases are escaping and then coming down into the communities and causing problems. So okay, so let's do a quick quiz question to wrap this up, see if this makes sense. And I'm just now realizing that's a terrible photo. It's very fuzzy, so I apologize. But this ties together both our identification of volcanoes and some of the hazards we've looked at here. So in this particular scene, you're asked to look at the volcano, make some observations to figure out what kind of volcano it might be, and then identify what the most likely hazard is here. So you've got, looks like 6 different options there. If you need to, you can go ahead and pause the video while you think this one through. And let's see what we've got here. So we've got this very steep-sided mountain off in the distance, capped with snow. It's very tall. It's steep-sided. It's fairly symmetrical in terms of its size and shape. So this would be a stratovolcano. And among those listed here, stratovolcanoes are one of our naughty volcanoes, explosive, and they produce pyroclastic flows. They can produce sticky lava flows, but they wouldn't flow very far. Lahars would definitely be a hazard because all the streams and rivers that flow away from this thing could be pathways for the lahars to travel down and into the low-lying communities. So the best answer there was E, stratovolcano and lahars. So there you go, a little fun quiz question to wrap up our episode here of the Geology 101 series. Hope you enjoyed this episode, number 13, unlucky number 13 on volcanic hazards. In our next episode, we'll look at processes related to weathering and erosion, and that will set the table nicely for what's to come down the road when we look at the next group of rocks, the sedimentary rocks. Thanks for joining me. Thanks for your support of the channel, and we'll see you next time. Take care.